In this lecture, we are going to discuss one key item, which I purposely left out of the previous lecture. And that is, how do we represent the states? First of all, we haven't yet discussed what kind of data we're going to use. Well, to reiterate one of the main themes of this course, your data can be anything in the world. It's your job to pick something useful and test it. In this course, for the sake of simplicity and comparison, we're going to use the same data that we used in our machine learning scripts. That is, we're going to use the previous day's returns for various stocks in the S&P. Okay, but now we have a problem. Returns are continuous valued variables. There are infinite numbers of them. In order to have a Q table, our states must be discrete. And in order for our Q table to fit into memory, we must have a finite number of states. So how can we tackle this issue? One simple solution is to use binning. The basic idea is this. Let's say we have 3 bins. We can say everything from -infinity to 0 goes into bin 1. Everything from 0 to 1 goes into bin 2. And everything from 1 to plus infinity goes into bin 3. So that's binning. You can take an infinite number of values and squash them down into a finite number of discrete bins. The next question you have to consider is, how do you define your bins? Obviously, the previous scheme isn't that useful, since most returns are very close to 0. So suppose we take the maximum value and the minimum value, and we split that up into, say, 10 equal parts. This is better, but it's still not ideal. As you recall, returns have distributions. Some values are very likely, usually the ones around 0, and some values are very unlikely. You don't want a special bin to take care of some extreme return that you only saw once. Conversely, you don't want to throw 90% of your returns all into the same bin. Then your model will have trouble learning anything useful. You don't want everything you see to be represented by the same state. So what we would like to do is define our bins according to frequency. That is, areas with higher frequency should have smaller bins, and areas with lower frequency should have larger bins. The bins on the left and right should extend to infinity. Luckily, there is an equivalent and easier way of saying this. It's simply that each bin should contain an equal number of data points. So that's the theory, but how do we implement this in code? Let's start with the easy part, and then we'll get to the hard part. If we know the boundaries of our bins and we have some value, how do we determine which bin it belongs to? NumPy has a function that does exactly this, called digitize. Here's an example from NumPy's documentation. We can see that the bins variable defines the boundaries of the bins. They are 0, 1, 2.5, 4, and 10. When we pass in x, we get back the bins 1, 4, 3, and 2, corresponding to the bins for each of the values in x. This makes sense. 0.2 is between 0 and 1, therefore it goes into bin 1. 6.4 is between 4 and 10, therefore it goes into bin 4. Now, what this example does not show is what happens when you go outside of the boundaries, which is definitely possible in our case. You're encouraged to try this on your own to verify the results, but here's what would happen. If I pass in -1, which is less than the smallest bin boundary, I get assigned to bin 0. If I pass in 11, which is greater than the largest bin boundary, I get assigned to bin 5. I think this makes perfect sense, since the full set of bins are then 0, 1, 2, 3, 4, 5. Okay, so next, let's discuss the hard part, which is how do we find the boundaries in the first place? Conceptually, this is pretty easy. All we have to do is sort the returns. Now we have an array of sorted numbers from smallest to largest. Since this is an array, we can look for equally spaced elements in the array. So as an example, let's say our array contains 100 elements and we want to split it using 10 bin boundaries. Since we want our model to handle values that can stretch to infinity, the boundaries for our bins should be centered rather than lined up with the smallest and largest values. So for example, I would have a boundary of 5, 15, 25, 35, and so on, up to 95. In this way, the first 5 values will belong to the same bin as, say, minus infinity, and the last 5 values will belong to the same bin as plus infinity. One last detail I want to discuss in this lecture is how we will represent the Q table. Since we'll be looking at the returns from multiple stocks, our state will actually be a tuple of integers, rather than just a single integer. Luckily, Python has the perfect data structure for this, which is the dictionary. As long as your object is immutable, you can use that object as a dictionary key. In our case, the state will be a tuple of multiple integers, and the action will be an integer. So we'll actually have a nested tuple of integers. This is immutable, which means we can use such an object as a dictionary key. So conceptually, the Q table is a table, but in our code, it will be an array indexed by objects, otherwise known as a dictionary. Okay, so that was a very brief lecture on how we will represent our states in the upcoming code lecture. Note that this is pretty complicated, so it's understandable if you don't understand what we just talked about, especially since there wasn't much context. However, I think it's useful for you to see everything twice. And so you should feel free to go back and forth between this lecture and the next lecture until you understand all the details. Better yet, as I always say to my students, if you don't like my solution, create your own. I'm only here to teach you the concepts and to give you an example implementation. It's not meant to be the fastest implementation, nor the most Pythonic implementation. It's the implementation that makes sense to me, and hopefully it makes sense to you. I think doing things the way I just described helps you to think through all the steps clearly and unambiguously. Your goal should always be to implement things in a way that's most intuitive for you.